Hi everybody, this is the third video in a series about finding the zeros of a polynomial function. If you haven't watched the previous videos on the rational zeros theorem and Descartes' rule of signs, you really have to go watch those because this video isn't going to make any sense. So, in the video on the rational zeros theorem, we learned that the possible rational zeros of this function were these 32 numbers. Now, there are only 16 numbers in this list, but we have plus or minus of every one, so we have 32 candidates. Then Descartes' rule of signs told us that the number of positive real zeros could be 4, 2, or 0, whereas the number of negative real zeros was definitely 0. This is one of the cases where Descartes' rule of signs is really powerful. Now, to be honest, sometimes Descartes' rule of signs isn't all that useful, but you see in this example that it can be. So, how are we actually going to find the zeros? Well, we're going to use synthetic division. You know that if you use polynomial long division or synthetic division and you end up with a remainder of 0, well, you have found a zero of the function. So, let's set up our synthetic division table. I'm going to leave a little bit of space because I know of some commentary that's coming up. So let's see. To make our synthetic division table, we have negative 15x to the fourth plus 50x cubed minus 69x squared plus 42x minus 8. Then we're going to leave some space. The remainders down at the bottom right. We really want this to be 0. That would be wonderful. And then our candidate, I like to put in a little box here to the left. So, which number do we choose? Unfortunately, we have 16 possibilities. We have all of the positive numbers from this list. At least we were able to get rid of the negative numbers. That's something. Now, I'm not going to make this video take 45 minutes and picking a bunch of numbers that I know are not going to work. What most people do is they try to do a little bit of mental math in their head, depending on how big the coefficients are. They'll do some scratch work on paper, do a little bit of trial and error, but I'm going to skip to where we find a candidate that works. So eventually you would try the number 1 because, well, the number 1's in our list. So let's go through the synthetic division algorithm. Hopefully these numbers don't get too big. So we have negative 15. Negative 15 times 1 is negative 15. 50 minus 15 is 35. 35 times 1 is 35. Goodness gracious, how big is this going to be? That's going to be negative 34. Negative 34 times 1 is negative 34. 42 minus 34, hey look, I told you it was going to work, is 8. 8 times 1 is 8, and that gets us a remainder of 0. So, make sure to pay attention to what these symbols mean. You've learned from the remainder theorem that when you see a remainder of 0, what that means is that f of 1, that's the number in the box, f of 1 is 0. You have found a 0 of the function. But more importantly, we learned this when we were looking at polynomial long division, we've also factored our polynomial. So our polynomial, the original polynomial, that was the dividend of our division problem. Our divisor was x minus 1, whatever number's in the box. X minus that is the factor that you discovered. So we have dividend equals divisor. The quotient is given in this line. So if we started with a 4th degree and we divided by a linear term, this quotient is describing a 3rd degree polynomial. So we have negative 15 x cubed plus 35 x squared minus 34x plus 8. So in this particular problem, you don't have to write this factored, but all of these things are connected, and it's definitely something that you want to keep in mind. So we found one of our zeros, x equals 1. That means there are 3 more to go because we have a cubic left in our quotient. So what are we going to do? Well, we're going to keep going. Now, it's nice, you don't actually have to go back to square one. You don't have to start all the way over and find another 0. Rather, you can apply the techniques that we've learned to this new quotient, which, luckily enough, we already have written right here in a synthetic division table. Draw another line. Our new remainder is going to be here. Our new test candidate is going to be over here. Now, unfortunately, we do have a lot of candidates left, and please realize that it is possible, now it's not true in this example, but it's possible that the number 1 is a 0 again. So you might have to test the number 1 again. It could be a 0 with high multiplicity. Multiplicity is the number of times that it's a 0, or the number of times this factor occurs. Now, once again, I'm not going to waste your time. This video is going to be plenty long enough. I know that the number 1/3 works. Worst case scenario, you have a little bit of trial and error, and there are some more theorems that can help us out a bit later if we want. So, we do synthetic division again. We bring down the -15, so that's -15. -15 times 1/3 is -5. 35 minus 5 is 30. 30 times 1/3 is 10. -34 plus 10 is -24. -24 times 1/3 is -8. And 8 plus -8 is 0. So we did it again. We found another real 0 of this polynomial. And again, just for emphasis, not that you really have to write this, but we've continued factoring this polynomial. We now have the factor x minus 1/3. And what's our new quotient here? It's in the bottom line, is -15 x squared plus 30x minus 24. Now, I'm sure you're already sighing, saying, well, I guess we're going to have to do this same thing again. Luckily, no. Notice that this factor is a quadratic, and you spent a significant amount of time in Algebra 1 and Algebra 2 studying quadratics. So why not use that information rather than doing more synthetic division, which in this case, once we get to the answer, you'll see wouldn't work anyway. So now we're going to take this quadratic factor, and we want to find out what zeros it gives us. So let's take that factor, and let's set it equal to 0. -15x squared plus 30x minus 24 equals 0. So now we're back in either Algebra 1 or Algebra 2 where we're solving a quadratic equation. I notice that all 3 of these numbers are multiples of 3, and I would like my leading coefficient to be positive. So at this step, I really want to divide by -3 on both sides. I think that would make life kind of easy. So this is 5x squared minus 10x. Remember, we're dividing by a negative, plus 8 equals 0. So you have to solve this equation. First, you would try to solve it by factoring. If you tried this, you would find that it does not factor. You could solve it by completing the square if you really want to. That's my preferred method most of the time, but just in case we're unfamiliar with completing the square, or it's been summer break since we've done that, you can always just solve a quadratic with the quadratic formula. So we have a is equal to 5, b is equal to -10, it's a -10, and c is equal to 8. So our last 2 zeros are going to be let's see, x equals negative b plus or minus the square root of b squared, which is 100, minus 4 times 5 times 8, so minus 4ac, all over 2a. I'm hoping there's enough room. So let's do some arithmetic. 10 plus or minus the square root of, let's see, 4 times 5 is 20. 20 times 8 is 160. 100 minus 160 is negative 60. Now, when you were in Algebra 1, you would stop at that point and say the equation has no solution. But after you learned about complex numbers in Algebra 2, we can simplify this a little bit more. So, off to the side here, I'm worried about running out of room. Let's see, 60 is 12 times 5, and 12 is 2 times 2 times 3. So 60 is 2 times 2 times 3 times 5. Keep that in mind when we're simplifying the radical. So, our next to last step, I hope, is we have 10 plus or minus. When we simplify the radical, we're going to be able to bring out a 2, because there's two copies of that factor. But we're taking the square root of a negative. So this is 2i square root. What's left underneath? There's a 3 and a 5, because we took both of the 2's out. 3 times 5 is 15, all over 10. And then, since both terms in the numerator are multiples of 2 and the denominator is a multiple of 2, we get this beautiful couple of answers. 5 plus or minus I root 15 all over 10 divided by 2 is 5. So this is 2 of our zeros. They're complex numbers, but they can still be zeros. If you were to take 5 plus I root 15 over 5 and you were to plug it into that original function and take several hours working that out, you would get 0 as the function value. So here are 2 of our zeros. And remember, the other 2 that we found were 1 and 1/3. So there you have it. That 4th degree polynomial had 4 zeros, and that pattern will always be the case. If you did this with a 10th degree polynomial, it would take a lot longer, and hopefully you'd end up with 10 zeros at the end. So anyway, your general technique, at least for now, for finding zeros of a polynomial is use your theorems to figure out where you're going, rational zeros theorem and Descartes' rule of signs. Use synthetic division to find zeros until you get down to a quadratic. Once you get down to a quadratic, you want to stop, because as you can see in this example, had we continued with synthetic division, well, we never would have found the answers because the last 2 zeros turned out to be complex numbers. So use synthetic division until you get down to a quadratic, and then find your last 2. Now keep in mind along the way, what you're really doing is you are factoring the polynomial. And if we really wanted to, we could write 2 more factors using these zeros, x minus one of these zeros. Now that wouldn't be a whole lot of fun, and my screen's full, and this video is way too long. Sorry, but it kind of had to be long. That's kind of the way dealing with polynomials is. So get some practice with this. Hope the video helped.